Hello, my name is David Lindquist. I'm an emergency medicine physician at Brown University in Providence, Rhode Island, and I'll be presenting lightning rounds with the abstract, Commercially Available Snakebite Device Reduces Bleeding During Repair of Laceration at a Non-Compressible Site. My co-authors, Dr. Jonathan Valente and Dr. Jason Hack, and I report no conflicts of interest. Dr. Hack authored patent 8641731, which is owned by Eastern Carolina State University. Dr. Hack receives no compensation from sales of VenomLock, the device that we used in this study. In background, tourniquets and pressure dressings save lives but have limitations. A commercially available snakebite device was pilot tested for novel use as a method of hemostasis and wound repair at a non-compressible site in a live swine model. The device is plastic with a hook and loop strap attachment, light and easily cleaned. Our aims were to test hemorrhage control and wound repair via a novel mechanism. We investigated the effect on blood loss after application of a snakebite device and whether wound repair with the device in place was feasible. This is a picture of the VenomLock device with the hook and loop strap attached. In its original design, it was intended to be placed on an extremity where a snakebite had occurred, providing adequate pressure to compress the lymph tissue only, localizing the snake venom and permitting the patient to be transferred to definitive care. In our study, we applied the device to a non-compressible site and attempted to exert adequate pressure with the hook and loop strap in order to achieve hemostasis and then attempt the laceration repair. The design was a controlled in vivo large animal model. The study was approved by the Lifespan IRB, Research Conflict of Interest Committee, and IOCOOK for the use of 10 crossbred swine as a model for hemorrhage control. The animals were sourced from an unrelated ongoing protocol that did not involve hemodynamic compromise. The incisions were 20 standardized thoracoabdominal incisions, 2 in each animal, made across the mammary line laterally at the costal margin, transecting the mammary veins. Each incision was standardized via a template to a length of 7.5 centimeters and down to the peritoneum without violation. For hemorrhage assessment, in the free bleeding phase, blood was permitted to flow freely for 30 seconds after the incision to account for anatomic variance. For quantification, the wound blood was collected with pre-weighed dry gauze, sealed in plastic bags, and immediately weighed. For the repair, the wounds were closed with 3/0 nylon by one of 2 proceduralists, either Dr. Valente or myself. All repairs used running sutures for consistency and speed. One proceduralist made incisions, applied the device if indicated, and performed the repairs, while the other proceduralist collected the blood during the free bleeding and repair phases. The sequence for control versus device repair was randomized for each animal. The proceduralists alternated tasks between animals to maintain consistency within each animal. Using a one-sample t-test, we compared the control groups versus the device groups. In the free bleeding phase, there should be no significant difference if the lacerations were equivalent. In the repair phase, there should be no significant difference only if the null hypothesis were true. This is a bar graph demonstrating our results. On the left is the free bleeding phase, on the right is the repair phase. The bars in black are the control group, the bars in gray are the device group. In the free bleeding phase on the left, you can see that there is no statistically significant difference in the amount of blood loss, demonstrating that the lacerations were equivalent. In the repair phase, however, there was statistically significantly less blood loss in the lacerations that were repaired with the device in place as compared to the control group. The mean delta difference in free blood during the free bleeding phase was 0.7 grams, no significant difference between groups. The mean delta difference in the repair phase was 3.1 grams, standard error 0.97, showing significantly greater blood loss during the control repair without device application. The effect size in blood loss was equivalent to a Cohen's d equals 2.6, which was a large effect size. Statistical power analysis demonstrated that the sample size of 10 animals was sufficient power to detect the significant effect, beta equals 0.82, alpha less than 0.05, one-tailed. In discussion, the initial study demonstrates that a commercially available snakebite device permits wound care at a non-compressible site, allows direct visualization of injury after application, and exerts adequate local pressure to improve hemostasis while performing the repair. A device that could establish hemostasis while allowing wound assessment and primary repair could be of value for providers of wilderness medicine, field medics, and others practicing in resource-limited settings. One limitation in this study was that the time to perform each repair was not measured. It is possible that the control repairs could have been performed more slowly than device-facilitated repairs, permitting greater blood loss from slower repairs. During the study, however, the proceduralist noted that the device made repair more awkward to perform, which may have led to slower repairs with the device in place. This potential confounder could be addressed in future studies by timing the duration of the repair. In conclusion, there was statistically significantly less blood loss during repairs with the device's application. This feasibility experiment demonstrates a commercially available snakebite device may be useful for hemostasis during laceration repair at non-compressible anatomic sites. The device's portability and reusability suggest utility in austere medical environments. Thank you.